Right, so now let's look at this idea of splitting methods, which is quite a common way of developing algorithms which, again, preserve geometric structure. So let me try to illustrate what I mean by this. Okay, so let's say you have a differential equation you'd like to solve, right? So suppose we wish to solve the following, right? So say dz dt is f of z, and I can write this vector field f into two separate vector fields, right? So let's say f1 of z plus f2 of z. Okay, and let's just further suppose that each of these separate vector fields are somehow easy to solve, right? Where sort of both, let's say dz dt equals to f1 of z and dz dt equals to f2 of z are completely integrable. Which basically means that they're analytically solvable, right? All right. So, of course, it is important to realize that just because these individual vector fields are completely integrable, analytically solvable, does not mean that the sum of those two vector fields is completely integrable or analytically solvable, right? So, note, this does not imply that dz dt equals to f of z, right, is solvable. Okay. All right. So that's sort of the setting it's like which we want. Okay, and the idea is that if you have a solution curve, it's like where f of z is this vector field, you want to write this at every point as some decomposition into, say, f1 of z and f2 of z. Okay. And the intuition, if you will, it's like of what splitting methods are to try to take compositions of the individual flows f1 of z and the individual flows associated f2 of z and compose them in such a way that you can approximate the solution of, it's like z dot equals to f of z, right, which is the sum of these things. Okay, and so let's look at a simple case. It's like to get a sense as to what happens. It's like when you try to do that, and what what happens, what basically prevents it from being the exact solution, if you will. Okay. All right. So specifically, I'm going to look at the case of linear ODEs. Okay. So you consider the case where dy dt is equal to, say, a of y, right? And you let a be written as some combination of two matrices, B and C, right? Then the splitting method defined by solving the first equation, which is dy dt equals to by, right, followed by dy dt equals to cy, right, is given by the following. Okay, so the numerical method is psi h of y is, okay, so y. Okay, so the exact solution of this is, if a linear system, is just the exponential. Right? So it's e to bh okay, applied to y, and then when you apply, it's like the second flow, it's e to the ch. Okay, so that's the numerical method, if you will. And then what you're comparing it to, of course, is e to the ah times y, right? So the exact flow, if you will, formally, is e to the ah times y. All right, so the local error is given by the following, right? So the local error yh is the numerical method applied to the initial condition y minus the exact flow applied to the initial condition y, which is of course nothing more than e to the ch, e to the bh minus e to the ah, whole thing applied to y. Okay. Yep. So let's look at really just the difference between e to the ch, e to the bh minus e to the ah and see what happens. Okay. Okay. So let's look at e to the ah minus e to the ch, e to the bh, right? So I can do a exponential series for each of these things. So this is the identity matrix plus ah plus 1/2 a squared h squared plus and so on, right, minus identity plus bh plus 1/2 b squared h squared and so on. Identity, sorry, that's c, right? Okay, plus bh plus 1/2 b squared h squared. Okay. All right. So you can of course consider this as a series. It's like in h, increasing powers of h. So let's just see what happens. Okay. All right. So it looks like the following. So of course we have to remember that a is equal to b plus c. Right. Okay. So so it turns out that the first order terms, it's like the zeroth order terms, are just identity minus identity, right? Which makes sense because it's like when h is equal to 0, it's like all these things are just the identity maps. Okay. Then the leading, the term which is linear in h is basically ah minus sort of ch plus minus bh, which is of course 0 because a is equal to b plus c. So the first, it's like non-trivial term is something which is quadratic in h. So let's see what it is. So this is h squared 1/2 c plus b squared minus cb plus 1/2 c squared plus 1/2 b squared plus big O of h cubed. Okay, so here you have to be very, very careful. It's like, because of course it's like b and c are matrices in general, and so you can't assume that you know, b times c is equal to c times b. So you can't assume that these matrices commute with each other. Okay, so one has to be very, very careful here. And so let's see what happens. So you get h squared 1/2 c squared plus 1/2 cb plus 1/2 bc plus 1/2 b squared. So you see this care to not assume that b and c commute. It's like by the fact that we have these two separate terms. Normally, of course, it's like if you were just dealing with regular algebra, it's like you would have collected these two terms together. Okay, so again, I'm not assuming b and c commute with each other, and you should not assume that. Okay, all right, so you have this. This is just coming from the expansion of c plus b squared, right? Plus then minus CB minus 1/2 C squared minus 1/2 B squared. Okay, so this term cancels out. This term cancels out with this term. This term sort of cancels, well, not really. Okay, so but you can collect these two terms, and then that becomes a minus sign. All right, so you just get h squared 1/2 BC minus 1/2 CB plus big O of h cubed. Okay. All right, so I can write this as the following. This is h squared over 2, the commutator of B and C. So the commutator of matrices is nothing more than, again, B times C minus C times B, and it measures the extent to which it's like the matrices commute with each other. So the commutator of two matrices vanish, right, if the two matrices commute, and then they're non-zero if there's, they don't commute with each other. Okay, so plus OH cubed. Okay, so let me say a little bit about this. So the matrix, bracket of B and C, right, is called the commutator. Of B and C. Right? So if the commutator vanishes, zero, right, then B and C commute. Since BC would be CB in the case where the two commute, right? So it turns out in that case, right, not only does this second order term vanish, right, but all the terms vanish. And what happens then is that you have the property that e to the c times h composed with e to the b times h is actually e to the ah. Right, so this is if bracket the commutator of b and c equals to 0. Okay, so what basically happens then is that this is basically saying that the splitting method is exact if it turns out that you can split this matrix A into two matrices which commute with each other. Okay, but in general, it's like this commutator is non-zero, which means that the leading order error term is big O of h squared, which means that this simple composition of or the simple splitting method is only first order accurate in general. Okay. So, all right. So again, if the bracket of B and C is equal to 0, right, then the splitting method is exact. Right, but in general, the splitting method is only first order accurate. All right, and so as you might expect, it's like this is just a case for linear ODEs. The next natural question to ask is, well, what happens if you have a nonlinear ODE? Okay, and we'll discuss that in a second. All right, so let me just stop here for now.